Tell us.
So, very good morning, Varanasi. Ma'am, I would like to introduce you first.
Okay. Sure,
So,
go ahead.
good morning, one and all present here, and a very good morning to our Tripti Jan ma'am, viewing us through YouTube Live. Welcome to optimal operation of power system incorporating renewable. I would like to introduce our today's very special. Tripti Jan ma'am is associated with Indore. She has received the BE degree in electrical engineering from Government Engineering. To obtain her PhD degree in electrical engineering from Miami. She also served as an assistant professor in School of Computing and about 2 years in department at Madhav Institute of Technology and for almost 11 years, I guess. And she is in IIT Indore since 2012. And is there applications in power systems, grid integration of renewable energy systems, and artificial intelligence applications to power system, power quality, and many credits like having a very good and it is a pleasure to receive the IETE Technomedia Award 2018 for Young Women in Engineering. So, ma'am, we are having you are the inspiration for many women in the central India and maybe in the country. So you give us lots of managing the research interest and I mean taking care of home along with that doing you are doing such a wonderful work in research area and take over to you. Please take over the session, ma'am.
Okay. So thank you, Niti, for such a nice introduction. I've not expected at all, but I think women can understand their problems together. So thank you so much. So today, welcome to all the participants. And even if any participant has any question, they can to me if it is allowed. Otherwise, he'll entertain these questions in the end of the session. So today I'm going to talk about microgrids. So first of all, I would like to say that microgrids, if you go back to the history of power systems, you will find out that microgrids is not a new thing, isn't? Because initially we have small isolated power systems, isn't? When the first power system was developed by Thomas Edison in 1882, it was a small power system, and then around the world there were so many small power systems developed, isn't? So all these small power systems, they were operating at their own frequencies, their own voltage levels. So we have initially different voltage levels, isn't? But later on, as the demand continues to increase, we realize that it will be good to interconnect all these small power systems so that we can have economical operation of power system, we can have reliability of power system. So with that concept, we moved ahead, and in that case, there was a single entity who was controlling the entire power system. It was able to manage the optimal dispatch of the power system. If any fault occurs, it has to be responsible. If it has to shed some load, it is deciding that which part needs to be shedded or disconnect that part. But it was a single power system. We interconnected different power systems. So now, again, the concept of microgrid has emerged, but the need was different, isn't it? So why this concept of microgrid came? We'll look into this. So our conventional power system, they were basically fossil fuel based power systems. And we all know that later on, initially we go on with the fossil fuel based power systems, but later on with the time passed, we realize that they have certain drawbacks associated with them. like the main problem which people realized later was they were emitting carbon emissions, due to which this global warming effect was coming up. And with the building up of large number of these fossil fuel based power systems, this effect was increasing continuously. So it was seen that this is having some environmental concern. It is having a bad impact on our environment. So better to consider some alternative options. So first reason was this one, although we all know about it. And with the increasing usage of more electricity powered devices and rising temperatures, we started using refrigeration. So this demand, it was continuously increasing. But with this increasing demand, we had limited stock of fossil fuels. All these three reasons together forced us to look for some alternative options, so that we find out, that we should go for, rather than this non-renewable energy sources, we should look for renewable energy sources, so that we have unlimited stock of those things. So the most appealing were solar and wind power. They were the most appealing renewable energy sources. But initially what happened, that the technology was not that advanced, and constructing or generating electricity through this was very, either in case if you want to construct at high level, the investment also very large, and it was not feasible actually initially. We can generate only a small amount of power through solar and wind. It was initially. Now we are like big solar power plants also. So basically, initially these renewable energy sources, they were called as distributed generations, because they were usually small scale power generations, which were in the range of tens of kilowatts to fraction of megawatts. So these power systems we cannot connect at the transmission level, because usually our conventional power system is in the structure, like we have big power systems, and they are transmitting the generated energy to the load centers, which are situated very far away. Isn't? So these renewable energy sources, because they are having small scale generations, we cannot connect at the transmission level. Otherwise, the losses will be more. Isn't? So it will not be efficient at all. It was seen that these small scale generations can be connected at the distribution network. So basically, therefore, these were called initially distributed generations. But so what are the other reasons for distributed generation? Because I'll go to the concept of distributed generation, which is more general rather than only renewable energy sources. It has become now more general. So before going to that, let us see that what are the other factors which motivated us to use distributed generation or to modify our conventional structure. So first was obviously ever increasing demand for energy. The second is like constraints on construction of new transmission lines. Even if you are able to construct big power plants, renewable energy based power plants, the main constraint was the environmental and economical constraints. Both are not allowing us to construct new transmission lines. Is it? So we cannot go with the construction of new transmission lines. So it is better that you connect them at the distribution level itself. Concerns over fossil fuel depletion, which I already discussed, and then inefficient transmission of bulk power over long distances. So although in the conventional, you have the large scale power plants located at some place, and then they are transmitting power to the load centers, which are situated far away from the power generations, but then power losses are more. So with renewable generations, it was not feasible option at all. Increased awareness of greenhouse. Another important point was liberalization of electricity industry. So as the deregulation of power system happened, the purpose was to introduce competition in the electricity sector, isn't it? So if we want to introduce the competition, then the players should be more, then only the effective competition will take place. So this, because these are small scale generations and their investment is also less compared to the large scale power plants, their construction time is also less. So it's not that more number of players can be introduced with the distributed generation. Because we were considering that we should, all this increasing demand concerns our fossil fuel, they were already there. So we were considering that rather than increasing the power plants, it is better to utilize our energy efficiently. So the focus was also towards energy efficiency. Further, as the technological advancements were made in power electronics technology and distributed generation technology, it became more attractive to use this new distributed generation sources. Okay. And one more point, with the time, as the time passed, the customers also, today's customers, they are willing to have more reliable electricity. They would like to pay more, but they want that the electricity should be available at any time. So these are the all factors which forced us to think about the distributed generation. So let us now go that what is the distributed generation. So distributed generation, as per this IEEE, initially I would like to say that initially there was no consensus on the definition of this distributed generation, because different countries were using different concepts. Some countries, they were considering that if you have small scale generations, then you can call them distributed generation. If you are connecting in the distribution network or lower voltage level, so according to voltage level also they were considering this is the distributed generation. And some countries, they were considering that if you have renewable energy sources, then you can call them distributed generation. But IEEE defines distributed generation as generation of electricity by facilities that are sufficiently smaller than central generating plants, so as to allow interconnection at nearly any point in the power system. So this is the concept, which includes, it is not necessary that you have only renewable energy sources, okay, but even the generation, any generation facility which is sufficiently smaller so that you can connect it at any point in the network, then that facility, so if like suppose you have small hydropower plants, small diesel power plants, you can call them as distributed generation. So this was the concept. And there was no agreement also on the maximum capacity of the DG unit, but usually it is ranging from 4 kilowatt to 10,000 kilowatt. And these DG units, they are mainly classified into combined heat and power and renewable energy type. And they require power electronic converters for their interface. So combined heat and power, it means that both thermal energy and electricity, they are generated from a single source of energy. So these are the DG technologies, which are, some are old technologies also, like reciprocating engine. It was the first among the DG technologies, but it was developed almost 100 years ago. If we come to micro turbine, then micro turbines, usually it comes in the range of like up to, I think, 1000 kilowatt. And these are the emerging classes of DG technologies. Then fuel cell. So fuel cell, although its development, I don't know whether you know about it or not, but the first fuel cell, it was developed in 1839 by Sir William Scrooge. But it didn't come into practical use that time. It came into practical use only in 1960s, when NASA used this fuel cell to generate electricity in spacecraft. And nowadays, like fuel cell is, different types of fuel cells are being developed. Okay, so research is going on this. And then we have renewable energy sources as the DG technology: solar, wind, micro hydro, geothermal, biomass, all these will come. So basically, okay, so the problems, these DG units, we cannot integrate directly in the main unit, because there are certain problems associated with them. So what is the problem? Whatever DG units they are using, they are mainly produce either a DC or a variable frequency AC. So you cannot connect directly into the grid. You require power electronic converters, basically inverters, so that you can interface them with the distribution network. Problem with the direct integration, we cannot connect them directly. Other problem with them is, we all know that they are intermittent in nature, and therefore the active power output from these DG units, especially RES based DG units, it is fluctuating always. But to ensure the stable operation of power system, it is always required that the supply and the load should always match, isn't it? Then only your system can operate stably. So the other problem with RES-based DGs was this one, that they are fluctuating and you cannot predict when it will not be available. It is difficult to predict them accurately. Other is because our distribution network, it was constructed, the conventional distribution network, it is constructed considering the point that power will be flowing only in one direction. But when we are integrating this RES-based DGs or DGs in the distribution network, this behavior changes, because now you have some sources in the distribution network which are injecting the power into the distribution network. So power flow problems will be faced because of this behavior. And because this RES-based DG units, they are integrated with the grid using power electronic converters, so the inertia associated is, see, the main the supporting point of this conventional power system, very important point, is they have large inertia associated with them, because we are using big synchronous machines. They have inertia associated with them. So small changes in load is always made because of this inertia. But here this becomes a major problem, because even if there is a small power imbalance, it may become unstable because of the lack of inertia. So all these are the problems of DG units. So we cannot integrate actually directly in the power grid. So because of to resolve these problems, so it was thought that we can, rather than integrating in the existing system, we should have a concept of a microgrid. So basically a microgrid comprises of low voltage distributed systems with DG units, storage devices, loads, and interconnecting switches. So the most important point of microgrid is that it can be operated in grid connected mode or on islanded mode. So that is the very important point. So what happens, it gives us flexibility actually. These two modes of operations, they provide us flexibility. So if you have, suppose you can see in the diagram that one circuit breaker after the nearby the microgrid, one circuit breaker is shown, and then the external grid is there. So point of PCC is there. So this circuit breaker allows us to disconnect the microgrid from the external grid whenever there is a fault in the external grid. So that fault we can stop to propagate in the microgrid. So, but disconnecting, what we can do, we can supply in uninterrupted power to our consumers. But there is the other side of the problem also, because the microgrid, it is incorporating small scale generations, okay, and loads. So even a small mismatch of power balance will create many issues. And to meet these issues, one of the good solution was that, because this renewable they are using, so you cannot predict whenever it will be available. Maybe it is available when you don't need the load at all, isn't? And they are generating a large amount of power. So the other thing was that we can have energy storage system. So even if it is generating, we can store that energy in our battery, and it can be supplied when the microgrid loads need it. Another flexibility which it allows is, we are not bothered. Suppose we are connected with the grid, we do not have sufficient power generation, but we are not bothered because that power can be obtained from the external grid, isn't? So we can exchange the power with the external grid also. And when we are having surplus power, but we do not have sufficient load, we can give back that surplus power to the external grid. So this allows the flexibility. Then you can see some controllers, is it? So these controllers are microgrid, because they are controlling the power exchange with the utility grid. Then they are controlling the output or the set points of the this renewable energy sources, energy storage systems, and loads also. So the everything inside this microgrid, they are controlled by these controllers. If there is some fault, either in the microgrid side or then it can be disconnected. Isn't the loads, maybe if you want to meet, it will decide like which are the critical loads, isn't? So they can supply to the critical loads. So everything is controlled by these controllers. So now we come to generic definition of microgrid. This was the general which I gave, but the US Department of Energy, it defines a microgrid, a group of interconnected loads and distributed energy resources with clearly defined electrical boundaries. See, clearly defined electrical boundaries that acts as a single controllable entity with respect to the grid and can connect and disconnect from the grid to enable it to operate in both grid connected and islanded modes. So with this definition, any DER installations we can call as microgrid. But the condition is, there are three conditions. Like one is, they should have clearly defined electrical boundaries. Then there should be a single entity. They should be able to disconnect and connect from the grid. The third point is, they should have the power generation capacity which is higher or just greater or equal to at least the critical load. It should be greater actually to the critical load which needs to be supplied to the in the microgrid. So in this figure you can see the different microgrids are shown. Isn't? Like if you go to the single customer microgrid, so there is one generator, one load, but it has this defined electrical boundary, and it is provided with the switches which can disconnect the other part of the grid. So this is a single customer microgrid. Second is, if you go this partial feeder microgrid, so some more generations are there, some more loads are there rather than single, and then they also have a clearly defined boundaries, and they are also provided with the switch which can disconnect and connect to the rest of the grids. So like this, so we have, this is why I was saying that microgrid is not a new concept. It is already existing, but only thing is we need to provide certain things so that it is able to connect to the grid and disconnect from the grid. This flexibility should be there, and it can, like if you consider, we have usually inverters, isn't, at home. So if you consider, we are not disconnecting it to the grid by our own, isn't? It is automatically, but that is also part of the microgrid. So this is basically the microgrid. It should have a flexibility that it can be disconnected, and it should have a generation capacity which is able to meet the critical load of your microgrid. That is the important point. So now let us have a look on major components of microgrid. So there are loads, DERs, smart switches, protective devices, master controller, communication, control, and automation system. To this detail. So the microgrids loads, they can be classified as fixed loads and flexible loads. So fixed loads, it means they need uninterruptible power supply all the time. So they cannot be altered, and they should be satisfied under any operating conditions. Isn't? So like hospitals, schools, industries, they load. So because they need uninterruptible power supply, we can never control this kind of loads. And therefore, these are called as uncontrollable loads or critical loads or non-responsive loads. The second type of category is flexible loads. So flexible loads, they are known as controllable loads or non-critical loads or responsive loads. Now, why controllable? Because it is not necessary with them that they need power all the time. So if we have some emergency conditions in the microgrid, these loads can be disconnected from the grid. In fact, they are called responsive loads because some kind of loads in this flexible loads category are like they can supply you power when you need it. Isn't it? Like if you consider storage systems. So storage systems basically, when they are charging, they become load. When they are supplying it energy, they become source. So they are basically electric vehicles or plug-in hybrid electric vehicles. So they become responsive loads. The other could be like we can have shiftable loads, isn't it? Which it is, if the conditions do not permit us to use those loads at that particular time, we can defer their usage. So like you are using washing machine, so it is not necessary. If the conditions do not permit, you can shift the operation to some later time when or during off-peak hours. So these kind of loads are known as shiftable loads. And the other variety is curtailable loads. All this comes under flexible loads only because they provide you the flexibility to change the load. So some are curtailable loads like residential loads. So if there is some emergency, then and it is not possible to meet those loads, they can be definitely curtailed. So all these types of loads are there in the microgrid. Then microgrid DERs. So DERs basically distributed energy resources, which not include DGs only, but the energy storage and responsive loads, because they also are supplying energy when we need in the grid. So DERs includes DGs, energy storage, and responsive loads, all of them. Then microgrid DGs, so we can classify them as dispatchable and non-dispatchable. So dispatchable means output can be controlled, but non-dispatchable, so mainly renewable energy sources come because you cannot control their output. When the input is available, it will generate. When the input is not available, it will not generate. So all renewable energy sources come under non-dispatchable units. Now, this renewable DGs, they have intermittent nature and they're volatile because the output is not available. It can fluctuate in any time. So to manage those two characteristics, it is important to have energy storage system in the microgrids. Usually you won't see any microgrid without energy storage system. So these energy storage systems play a very important role to ensure the reliable operation of microgrids. So its applications are like energy arbitrage. Energy arbitrage is basically when you have low price hours, you are storing the energy. But when you have high price hours, you are selling that energy back to the market. So this is known as energy arbitrage. Then we have frequency regulation and load leveling. So both these points will be clear in the next slide. So you can see that we need to maintain the frequency. If you see the first figure, like 60 hertz is the frequency we want to maintain, and the allowable band is 60.0 9.95. Within this band, the frequency should be maintained. So initially, the frequency was within this band, so we were not using ESS. So the stored energy was constant. But then what happens? The frequency starts increasing from 60.05. So frequency is increasing. So to maintain this frequency within the desired band, we can charge this energy storage systems. And as soon as the frequency comes within the desired band, again, we'll stop this charging. And then the later part of this figure, you will see that the frequency goes down below 59.95. So it means that the load is higher. So we need to supply more power. We can supply this energy through ESS so that this frequency is maintained within the desired band. So this is how frequency regulation can be achieved very quickly with the help of this energy storage systems. Then the next application is load leveling. So we usually want the load curve to be level. It should be as far as possible flat, although exact flat cannot be obtained, but it should be as far as possible flat. So like here we want that it should be maintained between 5 to 10 megawatt. So that is acceptable. So initially the load was less than 5 megawatts. So we started charging our energy storage systems. So it is maintained. So load we can increase at that time so that it is maintained within the desired band. And then it is constant. Again, the load goes up by beyond this 10 megawatts. So we are discharging, and again it comes within the. So with the help of this charging and discharging of the energy storage systems, we can maintain this load levels. So these are the very important applications of energy storage systems in microgrid. Then we have smart switches and protective devices. So protective devices, they identify the faults in the microgrid and they stop their propagation in the microgrid. And smart switches are to isolate some particular section of the microgrid. So like at the PCC, it can help in islanding by disconnecting the microgrid from the utility grid. So different kind of smart switches are required in the microgrid. Then master controller. So it is the most important part of the microgrid. He is the overall controller, and it is the responsibility of this master controller to ensure the reliable and economical operation of microgrid. So it performs microgrid scheduling in both grid connected as well as islanded modes, considering economic and security constraints. So it has to consider, it has to see the forecasting, load forecasting, generation forecasting, and according to these conditions, it has to decide the optimal dispatch of the dispatchable units. And if the non-dispatchable units are there, so according to forecast, he needs to decide that what will be the output of these DG units and what should be the set points of energy storage systems. So everything is to be done by this master controller. So it runs various kind of optimization algorithms to schedule this microgrid DG units. Then it determines the microgrid interaction with the utility grid. So basically, by this point, we mean that it exchanges the information with the utility grid and receives information of the utility grid. Listen. So, like, what is the status? All this generation forecast is managing, but all this information it needs to give to the utility grid also, so that they can decide how we'll operate. Listen. So, the status of this various switches, optimal dispatch at what time of various DG units will be there. So, all this information it is there with the master controller, but it needs to exchange this information with the utility grid and obtains the similar kind of information from the utility grid. If there's some scheduled maintenance also, so it needs to inform all these things. So it needs to decide also that when it will be operating in grid connected, and suddenly, usually it will be due to scheduled maintenance, maybe it may be happen that we have decided that it will operate at particular time in islanded mode, but mostly it will be due to the faults in the utility grid. So it is its decision to when to operate in grid connected and when to operate in islanded, when to switch from grid to island or from island to grid. So all these decisions are made by master controller, and it manages optimal operation of local resources. So it is the overall responsibility of master controller to ensure reliable as well as economical operation of microgrids. So, but to implement all these things, it requires communications and control and automation systems, so that it can ensure constant, effective, and reliable interaction among microgrid components. So these are the master controllers. So now all these are the components of microgrids, and we'll have a look over what benefits these microgrids are offering. Isn't it? So because most of the DG units which we are using in microgrids are mostly renewable energy sources, so it helps in reducing greenhouse gas emission. And because these DG units, they are they are integrated in the distribution network, so they are reducing the transmission distribution cost also, because they basically the load centers and generation, they are very close. They are in close proximity in microgrid, so it is reducing transmission and distribution cost also. Then it offers improved reliability by introducing self-healing capability at the local distribution network. So by self-healing means that the system which is able to know that it is not operating under normal or there is some problem in the system without human intervention, and then it is able to get back to the normal. Okay, this all is without human intervention. Then we call a system as self-healing. So by employing the modern technologies, these microgrids are usually considered to be self-healing if you employ all those modern technologies. Then because it is managing the local loads, so it can control voltage and frequency locally. So it provides better quality, power quality in comparison to our conventional power systems. It offers higher flexibility, controllability, and efficiency of operation due to all the previous characteristics associated with it, which we have discussed. Then there is bidirectional power flow between the utility grid and the microgrid in the grid connected mode of operation according to the which grid has power surplus. So power can flow from utility grid to microgrid or from microgrid to utility grid. Isn't it? And then it is able to supply reliable and uninterrupted power supply to critical loads even if the main grid fails. And ability to disconnect from the utility grid in case of voltage fluctuations and upstream disturbances. So we have a small part where the power can be supplied reliably. So all these are the benefits of microgrids. Now these microgrids, they can be classified as AC microgrids, DC microgrids, and hybrid AC-DC microgrids. So AC microgrids, basically they have one AC bus, and all these DG units we are connecting through these power electronic converters to the AC bus, and the loads are also connected through these converters to the AC bus, and this bus is connected to the main grid through PCC. So the advantage of this system is that because by default we have this conventional system is AC based system, so all the devices which are using they are designed on the basis of AC system only. So they can be easily, straightforwardly integrated in the network. But the problems are all the problems associated with AC systems, like reactive power requirements, reliability, synchronization. All these problems are associated with it. And another is because, see, if you see here, the more conversions, power conversions are required. With this photovoltaic panels, we are generating DC. Then you are converting, and you have DC loads. Most of the loads like laptop and all these electronic devices, they are mostly DC loads, but we are converting that AC back to DC, and then we are utilizing. So these are unnecessary conversions. So due to this, it is inefficient or less efficient, not inefficient, it is less efficient. Another type of microgrid is DC microgrid. So usually if DC microgrid is there, it should be preferred that those kind of sources should be connected where they generate the DC power only. So as to minimize the power converters, although DC to DC converters are very efficient in comparison to DC to AC or AC to DC, but this should be desirable. Those kind of loads, then only it will be more beneficial. But then we need to design different operating strategies for this. And next is like hybrid AC-DC microgrids. So hybrid AC-DC microgrids, so it has both types of buses, AC bus and DC bus. So what we planned here that, okay, whatever loads which we need, which the AC loads, they can be connected to transformer here, and AC power generations, all those AC kind of sources and AC loads requiring AC power should be on the AC bus side, and the power generations generating by default like DC power and this loads which require DC power should be on the DC bus side. And then both this AC bus and DC bus, they can be interconnected through bidirectional AC-DC or DC-AC main converter. And so it looks a good concept. The operational strategies will be very complex and it needs to be designed. So that is a problem. So research is going on in this direction also. So let us have a look on what are the main issues in microgrid. We have seen already that how does it operate, but then what are the main issues? So microgrid scheduling. See here, because we are having in the microgrids responsive loads also, you never know when these loads will supply energy or when they will take energy. So there is load uncertainty, and because of the use of renewable energy sources, there is source uncertainty also. So both this source and load uncertainty, so how to take them into account? While deciding the operating points or output of various units, various DRs involved in the microgrids, it becomes very difficult when there is both kind of uncertainties, load as well as source uncertainties. So that is one of the main issue. Second is demand side management. So this demand side management, it includes both energy efficiency as well as demand response. So the main part in demand side management, if you consider the demand response, is we are allowing the consumer to change their electricity consumption according to the situations available in the system. They can be price-based system also. So maybe the consumer do not want to pay more. So during the high price period, it is changing his load pattern. And so they can provide actually both things. One side is uncertainty, is obviously, but without much investment in the system, it will provide you to manage the load very efficiently also with the less capacity, generation capacity and energy storage also. So it can be managed, but the problem is how to involve the participants, consumers in demand side management. So you need to design some appropriate scheme so that consumer is willing to participate in this demand side management. So we need to develop some kind of schemes which attracts consumers that they should participate in demand side management and they should be willing to change their load pattern according to our grid situations. So that is the one issue. Then the other part is how to ensure reliable operation, especially in islanded mode. See, when the microgrid is operating in the grid connected mode, all the responsibilities being taken care of the utility grid. So all the loads will be supplied efficiently in this island grid connected mode of operation. But as soon as it is disconnected from the grid, then it has its own resources only. So at that time, to ensure its reliable operation, it becomes a bit challenging. So we need to work on that. Other part is redesigning of the protection schemes. So basically, if we see our conventional system, so in conventional system, what is happening whenever the fault is occurring, the fault current, it becomes usually very high. So you can easily distinguish the normal current and the fault current. The fault current is almost 10 times higher. But because we are using these power electronic converters in the microgrids, due to this usage of this power electronic converters, the fault current is only twice of the normal current. So then we are using the relays and this, so it becomes very difficult for them to distinguish between the fault current and the normal current. Okay. So we need to design different kind of protection schemes which are able to distinguish between the normal current and the fault current. So a lot of work is going on in this direction also. Then we need new voltage and frequency control techniques in the microgrid and new market models, because the market model should be such that it encourages the participants, renewable energy generation, to invest in renewable energy sources and participate in the market to bid. So this is another part. And then we have this development of market and control mechanisms exhibiting plug and play feature. So basically by plug and play, I mean that the DERS locations, it should be location independent. You can put this DERS anywhere in the microgrid without re-engineering. So like once it is designed with the control, you can put it in any place in the microgrid. Okay, it should not be location dependent. The controls should not be location dependent. So these are the main issues where a lot of research is going on. And these are the challenges in the microgrid protection and control. So as I told you that bidirectional power flows, so the power, because we have the sources in the distribution network now, so the bidirectional power flows will be there. And because of this, if the power flow is reversed, then reverse voltage gradient will be there. So different kind of challenges will come. So we need to have develop the protection scheme such that it is capable of dealing with bidirectional power flows. Then reduction in fault current capacity. So then protection scheme should be able to deal with that also. It should be able to discriminate the device because the fault current is very less. Then islanding is there. So islanding detection, so it should be detected very quickly as soon as the islanding happens, because it will not be informed. Now, if it is occurring due to fault, the VCC point, it will automatically disconnect your microgrid. So if it is disconnecting your microgrid, you should be able to detect that we are operating in the islanding mode, and the controller should be able to identify the control strategy so that the reliable operation is ensured. Then you have stability issues, because if the stability issues are actually mainly in the islanding mode only. We don't need to worry about the stability issues in a grid connected mode, because the main grid will take care of it. But in the islanding mode, even a small imbalance may cause the system to operate an unstable manner. Then microgrid modeling. So usually in the power system, conventional power system, we assume that we have three-phase balance system. We model loads as constant power loads. We ignore network dynamics. But because microgrid is a small system, we need to consider this high power dynamics, low frequency dynamics, and high frequency dynamics of inverters. Then network dynamics, load dynamics. All this will play a role. So we need to model the microgrids also appropriately. All these features need to be considered. Then the inertia is low because of this power electronic converters. We have low inertia and we don't have any moving these machines also. So we have low inertia in the microgrid, which basically may cause instability even during the small power imbalance. And uncertainties is also there, how to deal with uncertainty posed by these loads and challenges. I'll come to the control system because that is the most important part in microgrid. So the objectives of control system are when the microgrid is disconnected from the utility grid. But as soon as the fault is disappeared, this microgrid needs to be reconnected to the utility grid. So that time we need to synchronize with the utility grid. So you need to coordinate properly the output of all the DG units so as to synchronize the voltage and frequency of the microgrid with the main utility grid. So it is a very difficult or challenging situation. So the control system should be able to achieve this. So different controllers or different control strategies needs to be used. And then to maintain power balance between the generation and the load, particularly in island mode of operation, maintain stable voltage and frequency in the microgrid, maintain the power quality injected in the quality of power injected into the utility grid, harness maximum power from various renewable energy sources. So this control strategy, it is implemented at two levels. One is at system level and is at component level. So microgrid central controller, so it is the system level. So it is the overall responsibility of this microgrid central controller who will ensure the reliable operation of microgrid. And then you have individual controllers like for energy system, for load, and for microsource. So you have individual controllers there. So this microgrid central controller, so as I told initially also, that it provides power set points for the DG units, economic scheduling of the various DERs it performs, it controls the peak load, non-critical loads during islanding, minimize system losses, detect islanding conditions based on the measurements at the PCC, then initiate resynchronization with the local controllers when the grid is restored. So to monitor power flows through local generating units and the PCC to make islanding decision. So all these are done by the microgrid central controller. So major tasks are done by microgrid central controller and it coordinates with the local controllers also. Now these are the micro sources control methods. So all the DG units have this kind of controls. So one important thing is control strategy here depends whether the microgrid is operating in the grid connected mode or in the islanded mode. So basically in grid connected mode we have PQ control. Okay. So PQ control, so like the P and Q reference limits will be decided by the utility grid and it will inform the microgrid that these are the set controls. So these set units are decided by the utility. If it is grid mode, it will operate in PQ control. But if the microgrid is operating in islanded mode, then there are two control strategies, droop control and V-bias control, which are similar to primary control and secondary control of the conventional power system. So droop control, basically it comes into the picture when there is a small change in load. Okay. But if there is a large disturbance, then V-bias control is there. So in droop control also we have two types of controls, PF control and QV droop control, as we used to have in conventional power system. So PF droop control, it controls the frequency by regulating the active power output of the DG unit. And QV droop control, it regulates the voltage by controlling the reactive power output of the DERs. We have energy so Niti,
Yes,
how much time do I have? Yeah, how much time do I have? Shall I finish it? 5 minutes?
Yes, ma'am.
Okay. Yeah. So we have this energy system and load controllers. So we should design the control strategies which allows this energy storage systems to absorb or release power quickly, so that the influence of temporary mismatches of power balance can be reduced in the microgrid. So basically, we need to control the charging and discharging of the storage system, and which will depend upon the grid operating conditions and state of charge of the hybrid storage system. Okay. And then load controller should be designed to shed the non-critical loads in case of power imbalance, particularly in the islanded mode of operation. So you must be understanding main issue comes when the microgrid is operating in the islanded mode. So now there are control hierarchies. So we have three levels of three hierarchical. This hierarchical structure has three levels. One is primary level control, secondary level control, and tertiary level control. So basically, primary level control is what we have seen as DRUP control. So it is controlling this power sharing and voltage and current control locally of the individual DG units it is providing. So that is the primary level control. And basically, all these controls, they have different, they are categorized based on their response time and the time of scale. So it is the fastest one. This primary level control, it operates very quickly. And usually it operates in the range of like 10 to 100 milliseconds. So it is so fast. And then comes the secondary level control. So basically this secondary level control is, we can call it as energy management system. So it operates in the range of I think 1 to 10 seconds. This voltage or frequency restoration, power quality control, and power flow or synchronization control. And the third level comes is tertiary level control, which performs this economic dispatch and operation, microgrid supervision, and generation forecasting. So the time of a scale of operation of this tertiary level is in several minutes. So this kind of controls are present in the microgrid. Then we have like secondary controls. So different architectures are used: decentralized, centralized, distributed, and hierarchical control. These things. So if you see the decentralized control, so here each individual DG unit, IIDG1 is basically inverter interface DG units because they are interfaced through inverters and they have this primary control. So the decentralized control, you can see that each primary control is connected with a secondary control. So this is local and it utilizes local measurements. So the main drawback of this kind of a scheme is like the proper coordination is not possible among the various IIDG units because you are not aware of the control strategies or conditions of the other unit. So that is the problem. Then we have centralized control of microgrids, but it requires a good communication infrastructure because there is only one control which coordinates with different IIDG units. So it is receiving information from the primary control of all the IIDG units available and then informing them the controls. So this communication infrastructure should be good. Then we have distributed control of microgrids. So basically, it is an addition to the decentralized controller that it is secondary control. It is similar to that, but there it was not. The secondary control unit were not able to know the conditions of the other IIDG units. So they are now, with the help of they are receiving the information about the about the other IIDG units also. Then we have hierarchical control of microgrids. So this hierarchical control, it requires both secondary control as well as centralized control. So if any one control fails, the other one is there to take care of the thing. So these kind of control structures are there. Then a few islanding detection issues. It is very important. In islanding is the situation in which a microgrid becomes electrically isolated and from the utility grid, and it may be intentional and unintentional. So if it is intentional, then we already know that when we are going to islands, so we'll make all the arrangements accordingly. But if it is unintentional, then it poses severe challenges. So it is very important that if it is unintentional, you should be able to identify that islanding has happened so that the control strategies also can be changed quickly. So the main thing is if the islanding happens, then the microgrid's electrical characteristics will change significantly. So the main philosophy for islanding detection is that to monitor the active, voltage, frequency, and impedance of microgrid and active as well as reactive power output of DGs. By monitoring this, we can have Now, there are several techniques. I'm not going into the details of this, but like remote detection and local detection. So remote detection utilizes communication infrastructure and some kind of communication it uses to detect the islanding, and local detection. So it basically monitors this voltage, frequency, and impedance, and based on that, it decides whether the islanding has happened. So stability is very important. So this, because of the time constraint, I won't go into this detail, but it is actually similar to the stability which we see in the conventional power system. Only thing is few more, few more like local oscillations will be more in microgrid because of the presence of this power electronic converters, energy storage system, and different controls. But the issues are like similar. And these are the reasons which may cause different kind of instability in microgrid, and shows the stability improvement method. So basically, this is not a big deal because we already know about the stability improvement methods of AC systems also, and we have discussed here AC microgrids. So this can be considered. So now, because the purpose of this presentation was mainly to guide to the audience, like what are the different possible areas in which the research can be carried out in the microgrid. So as I told, it will summarize here that development of appropriate techniques are needed for detection and isolation of faulty portion in microgrid. Development of suitable protection schemes are needed to deal with the bidirectionality of power flows in microgrid. Then improving robustness and adaptability of the control techniques to topological and parametric uncertainties. Then developing control schemes that function for both grid-tied and islanded modes of operation of the microgrid and provide a smooth transition also. Because see, we talked here only about the grid-connected and this islanded mode, but there is one more from one of the mode to the other mode. That time also, this should be some strategy should be there which is able to control the transition. Okay. Then development of suitable control and management strategies of energy storage system in the microgrid and high speed islanding detection algorithms. So this is also one of the very important area, islanding detection algorithms, where many signal processing algorithms may be used to detect islanding quickly. Okay. So these are the areas. And thank you. Now I can answer questions if there are any.
Thank you so much, ma'am, for the wonderful lecture on microgrids. You have touched every basis of microgrids right from the history and still the recent researches. I hope the participants have many takeaways from this session. So we'll be taking the question answer session now. Mr. Mahadev Talavar is asking, can you bring up the case studies in India about microgrids?
See, actually, they are going on. I don't have right now any details. Different structures, like what I have gone through while searching that whether there are any microgrids, because if we consider this, they are specifically for rural areas, isn't it? So I think 2-3 years back only I searched that if there are some microgrids constructed like this, isn't it? So there are many agencies which are doing this. They are not popular. They're doing specifically this for rural rural areas, isn't it? But as of now, any specific case study for microgrid, I'm not aware.
Okay, ma'am, there is a request. Can you please stop share so that we can have the better speaker view?
Okay.
Yeah. Thank you, ma'am. And there's another question from Sudha Bhutra, ma'am. She is asking for bidirectional flow. For bidirectional flow, what are the measures to be considered?
See, basically, our conventional this protection schemes, isn't? I'm not working in the protection scheme, so I do not have that idea. But only thing is like our conventional scheme, it is designed considering that the current will be flowing in only one direction, isn't? So if the current is coming from the opposite direction, it may cause certain implications. So that is the issue. But because I'm not working in the protection side, okay, difficult.
Okay, ma'am. Next question is from Mr. Shiv Kumar Nayak. He is asking, do microgrids increases the reliability in microgrid? grid?
Yeah, definitely. Because see, you have, if a fault occurs in the part, maybe we can isolate the small part. Okay, that particular section may be isolated, but definitely microgrid will increase the reliability in comparison to our conventional power systems.
Okay, and the next question is from Dr. Gopal Palli Naresh. He is asking how to control voltage, frequency, and phase sequence of the power generated using renewable energy sources in a microgrid.
The different control strategies are there. You think you need to go into the specific details, like different this local control. Whatever power electronic converters we are using, we are not using them without any voltage control. So small perturbations can always be controlled. There are this by this QV and PF. Okay, this local this to maintain the frequency and voltage in the specified limits. We are always using this PF control, troop control. But if the the change is large, then you need to devise a strategy particularly for that.
Okay, thank you, ma'am. And one more last question is there. What could be the research area and optimal location and sizing of DG? If you can please elaborate.
See, I think lot of research has already been done in optical sizing of DGs. I think 10 years back also this was going on. So you need to formulate optimization problem and try to solve that problem with some good optimization technique. The way I'm saying, like the people have done, but where you need to place, you need to study about that area also, that how much potential that area is having, and after that you will start doing that.
Okay, thank you so much, ma'am. Thank you for the session, and I would just like to share a certificate. This is the small gratitude from our institution.
Okay, thank you so much.
Can you see this, ma'am?
No. Yeah,
Yes.
sure. Yeah. Thank you so much.
So thank you so much, ma'am, for the wonderful session today. I hope all the participants have discussed a lot about microgrids regarding the recent research areas. So I hope the participants will get very much insight of that. And I thank you all the participants for joining. This is the last session of our STTP, and we are looking forward to joining you us in the next STTP of from our department, which would be on electric vehicles. So thank you, ma'am, once again. And now I would like to invite Dr. Shefali Jan, HOD EX department, to extend her vote of thanks.
Good morning, ma'am. Thank you, Tripti ma'am, for such a nice session about microgrids. You have also mentioned in the end about the research areas for the microgrids. Thank you so much, ma'am. So today that was the last session of our STTP. On behalf of Department of EX, I would like to express my sincere thanks to all the participants who have joined us across the India and other countries too. I hope that all the sessions were useful for your field of research area. Last but not the least, I would like to thank all the members of the organizing committee for their outstanding performance in the conduction of STTP and for making this STTP a grand success. Thank you so much. Thank you again, Tripti ma'am.
Yeah,
The participants, all the participants.
Good experience to give a talk here.
Yes, ma'am. Yes, ma'am. And thank you all the members of organizing committee. So in continuation with this, I would like to repeat that the Niti ma'am has already told about that we are again going to organize one week STTP on electric vehicles. That would also be AICT approved. So I would like to request all the participants, please do register for the same. Thank you. Thank you so much.
Okay.
Thank you, ma'am, for being so humble and accepting our request and be available.
It was
Thank you so much, ma'am.
experience. Okay. I enjoyed it.
Be looking forward to seek your guidance in future also. So we'll be in touch with you. Thank you from
Sure.
EX Department
Okay.
of Science. Thank
you,
you.
ma'am. Thank you, ma'am.
Okay.
Signing off now. That is all from our side for this session. Thank you, everyone.